Okay guys, welcome back. So in the last video I explained to you the basic what is meant by basic thermodynamics. I started the topic of basic thermodynamics and I explained to you what is the work done by a gas. Alright, so that is about the work done by a gas as I mentioned in the last video. So as I mentioned in the last video, I'll be explaining to you about the internal energy of a gas in this video. Alright, so internal energy of a gas. So the internal energy of a gas is internal energy of an ideal gas is the kinetic energy of the thermal motion of its molecules. So it's due to the kinetic energy. Alright. So let's take an example. Internal energy. Internal energy. Right? So if you have some system like this, if you have some molecules here, say 1 or 2 molecules, right? Molecules like this inside the system. So this is a gas, right? Gas system confined by some boundary. So if I take the initial temperature to be Ti, and if I increase the temperature by some value, this system will be like this. You know from the KTG, the kinetic theory of gases and the other concepts, that when you increase the temperature of an ideal gas, the kinetic energy of the system will increase, as well as due to the kinetic energy is increasing, the speed of the system, speed of the molecules, of all the individual molecules will also increase. So I'll take the same molecules like this. Right, and the final temperature to be TF. So you know that TF is greater than Tn. So KEF is greater than KEI. K means the kinetic energy. So you know that the internal energy, as I explained before, the internal energy of a gas, of an ideal gas, is the kinetic energy of the thermal motion, right? Thermal motion of a gas, of its molecules. Alright, it's also all due to the thermal motion. Alright, so internal energy is due to the kinetic energy, means internal energy should be of some proportionality. Internal energy should be of some proportionality to the kinetic energy of the molecules. Right, so you know that from the video I explained about the kinetic energy of a gas. You know that we found that the kinetic energy of a gas was E equals what? We found that the kinetic energy of a gas is 3 by 2 times RT by N, right? 3 by 2 times RT by N. So E is the kinetic energy, sorry, E is the kinetic energy, and R is the universal gas constant, T is the absolute temperature, and N is the number of molecules. So if N is the number of molecules, if I take simple N, the number of moles to be the number of molecules divided by Avogadro number. So N will be N times L for 1 mole of gas, if you take the Avogadro number. So what you can say is that E is 3 by 2 times RT times, R delta T times N. Right? So you can say, right? E equals 3 by 2 times in R delta T, right? Alright, so the kinetic energy of this gas, kinetic energy of this gas is the internal energy. So the internal energy of this system is 3 by 2 times N times R times delta T. Alright. So if the internal energy is so, right? Internal energy is so, the internal energy of this system should also be of this value. Internal energy the system is also 3 by 2 times nr delta T. Right? 3 by 2 times nr delta T. So this actually normally this equation is not used in many concepts. Right? 3 by 2 times n times r delta T is not normally used in concepts. It's used as a deduction formula. As a deduction formula that I will explain in the next video about the when I am explaining about the first law of thermodynamics. So let's take a simple example. Let's take a simple example in which you were given that there are 3 moles of a gas. 3 moles of a gas which is initially at a temperature of 300 kelvins, and you increase the temperature to 400 kelvins, and we have to find the internal energy change of the system, or the value of delta E. Alright. So for the first system, so you know, if I take a system like this, right, that I am taking n equals 2 moles. I'll take n equals 2 moles, right? It's easy. N equals 2 moles, and the first temperature of Ti to be 300 Kelvin and Tf to be 400 Kelvin, right? So you know that from the equation we just derived, delta E is equal to 3 by 2 times n times r times delta T. So this is equal to 3 by 2 times n is 2, r is 8.3 times delta T. Delta T is the difference of temperatures. So it will be 400 minus 300, which is 100. So these two cancel. So it will be 3 times 830, which is 0.924 joules, or approximately 2.5 kilojoules. Approximately 2.5 kilojoules. So that is energy change when you change the temperature by 100 kelvins for a gas of 2 moles, right? So that's a huge energy change, right? When you change the temperature by 100 kelvins. So 100 kelvins is the change of temperature by 100 kelvins is the same as the temperature same as the change of temperature by 100 degrees of Celsius, because it's a scale that we are using. So you'll get a huge energy change according to this equation. But this equation is not normally used in the concepts of laws of thermodynamics. In order just to explain it to you, I use this equation, right? In many concepts it's not used. So in the next video and the videos thereafter, I'll be explaining about the laws of thermodynamics. So laws of thermodynamics heavily depend upon the energy supplied to a system or energy released by a system. That means the energy change, the internal energy change, and the work done, right? Work done by the system or work done on the system. So all those scenarios will be talked in the next video. So in this video I talked about the internal energy of a gas. So internal energy of a gas and the work done by this system will be used in the next concepts or in the next videos in explaining about thermodynamics. So thanks for watching this video, and see you then.